Hi, everyone. My name is Michael Aideloje, Lead Product Manager, Public Cloud FinOps at Bayer.
And I'm Aviv Revach. I'm the co-founder and CEO of Adaptive6, also serving on the governing board of the FinOps Foundation. Very happy to be with you here today.
So, today I'm going to speak to you about how Bayer eliminates inefficiencies in cloud, runtime, code, and AI workloads with Adaptive6. So let's get started.
Perfect. So 2026 state of FinOps, number one priority is still and has been workload optimization and waste reduction. This has been the case for the last 3 years in a row. Obviously, with AI growing, the next frontier is actually FinOps for AI, and that has been gaining a lot of momentum. And obviously, the intersection between the two, which is AI waste, which a lot of organizations are now highly focused on. So there is the common waste we're used to, there is the hidden inefficiencies within the cloud, and there is the AI waste that is now getting even more momentum. So as we get started, maybe just a quick word about Adaptive6. So essentially, we're in the space of cloud cost governance and optimization, providing agentic governance and optimization of cost across cloud, code, runtime, and AI. And what that really means is that we detect more than 400 different types of inefficiencies, waste and shadow waste, these hidden inefficiencies beyond the obvious, across the multi-cloud environment, Kubernetes, data cloud like Snowflake and Databricks, as well as AI workloads. And we not just find the problems, but we actually focus on fixing them and empowering engineers to fix them by driving that remediation workflow, providing them with the code fixes, shifting left, and even preventing them from making the same mistakes over and over again. So, talking about cloud cost governance and optimization, it's a methodology that falls under usage optimization within the FinOps framework, right? And it really talks about the detection, remediation, and prevention of waste. Now, there is the common waste we're all used to be talking about. This was like a few years back, like unused resources, rightsizing, that's good. Last year, actually, when we also presented here, we talked about shadow waste, these hidden inefficiencies beyond the obvious that typically evade standard tooling, and that has the potential of a lot of millions of potential savings, and Michael is going to talk a lot about that. And then the next frontier is really application inefficiencies. And this would be also a key topic in today's talk. So it's not just anymore about the infrastructure layer, but actually what's living within the application itself. How do we actually tap into insights into the applications themselves? All of these wastes that we are talking about, whether it's waste, shadow waste, and application inefficiencies, could be detected in cloud, inside the code, where you want to find some more architectural inefficiencies. And then if you're looking at application inefficiencies, the real place to look at is to actually look at the runtime layer, to actually shift right and see within the application. Typically, it's being done using a runtime sensor. So you basically deploy a sensor within a machine, within a VM, or as a pod, and you get more in-depth insight into what the application does. So we're going to start with Michael talking about shadow waste, and then the second half of the talk is going to be about these application inefficiencies.
So let's take a moment to expand on shadow waste. This refers to inefficiencies beyond the obvious. The kinds of things that your cloud providers or your common FinOps tools often miss out on. Some examples include complex service misconfigurations. For instance, DynamoDB provision mode versus on-demand. Which do you choose? Another example has to do with hidden features within the cloud that most times engineers are unaware of. Architectural flaws is another example. like having cross-region storage data transfer for no reason. Production and dev mirroring. This is actually really common. Like, why would you have why would you have a premium app service plan in a non-production environment? You can typically just settle for a standard one. These are all good examples of shadow waste. So, let's dive into the fun stuff. We're going to look at Bayer's case study with Adaptive 6 CCGO. First of all, some background. Some of you might not know who we are, but Bayer is a massive global enterprise spread across the globe. We have a presence in almost every region of the world. Our key vision is a world where there is hunger for none and health for all. How do we support that? Well, we have multiple applications with thousands of cloud accounts. With those thousands of cloud accounts are spread across a multi-cloud environment, more specifically AWS, Azure, Google. It includes a mix of both modern and legacy workloads across our 3 core divisions, specifically pharma, crop science, and consumer health. We also have affiliates as well. Some of you might know about the soccer club Bayer Leverkusen, Bayer 04, or Nofia, as the Germans would say. It is also considered an affiliate of ours as well. All right, now that covers the organization. Now looking at the core FinOps team. We have a Cloud FinOps team of 12 individuals located in different regions around the world, some of who are actually here with us today, spanning from Europe. We even have some in Asia and across the world as well, China. I come from a mix of finance, I do have a background in finance and accounting, and also cloud engineering, most recently being like the last 5 to 7 years. I blended that together, and with FinOps, I was able to leverage those 2 skill sets. The team is comprised of, again, 12 individuals from different backgrounds, some from procurement, some from finance, and we also have a strong data and cloud engineering team. So that's the FinOps team. Key stakeholders that we usually relate with include cloud unit product teams, which is essentially a product team for every cloud provider. So we have an AWS engineering team that's specifically just the infrastructure team for AWS within the organization, same for Azure and GCP. We have FinOps principles spread across, embedded in every single IT platform within the organization. So essentially, we operate a hub and spoke model there. So all of these individuals, including procurement and finance, constitute what we call the Cloud Cost Governance Board. We meet on a bi-weekly basis to talk all things ITAM, FinOps, SaaS, cost management, you name it. So we utilize FinOps tooling, like most of us here, for cost transparency. We have a Power BI dashboard that we use to visualize cost down to the account level, down to the service level. And we also have automations in place that we use to do what I like to refer to as high-level cost optimization. That is, we have automations in place that tracks, identifies unused resources such as unattached disks, unused IPs, old snapshots. They're identified and they're automatically deleted. We do this on a monthly basis. So We got the low-hanging fruit covered. Now, we suspected that there are huge amounts of hidden shadow waste and application inefficiencies that were going completely undetected. The bigger challenge for us was that even when we found this waste, remediation lacked the necessary engineering context. It involved complex manual work, which included a development of infrastructure as code fixes, and simply, it couldn't scale across a large enterprise like ours. We needed a partner to help us move from just visibility, which we pretty much got covered, to true scalable governance and optimization that will drive engineering action. So the implementation of Adaptive 6 Cloud Cost Governance and Optimization was truly transformative. Thanks. It helped us regain complete control over our multi-cloud and AI spend, moving from merely suspecting the waste to truly uncovering it. We found tens of millions of euros, yeah, we use euros because, European company and all, in shadow waste that our O2s just couldn't touch. Crucially, Adaptive 6 didn't just uncover the waste, it provided our engineering teams with the rich technical context that they needed, with actionable code-based recommendations that they actually needed too. The use of AI and automations massively accelerated our remediation cycles. We integrated this result into our centralized reporting to track progress and drive celebration of team success. The bottom line, this exceeded our most optimistic expectations, achieving a remarkable 20x ROI in less than the first year of going live with Adaptive 6. The core part of this success was obviously culture. We didn't just deploy a tool and sit back and let the engineers do what they normally do, which is ignore us. We launched a movement. The first step was enable our engineering groups running multiple webinars across teams with hundreds of participants. As you can see here, we usually have these quarterly, what we like to call info sessions, where we reintroduce Adaptive 6 to our engineering teams. We encourage them to go in, look at the issues, the recommendations from Adaptive 6, and also we have a Q&A session with them, basically answering any questions we have. Oftentimes we'll invite members from Adaptive 6 to sort of answer questions there and provide additional context to this. You can also see that very much like engineers, no one's camera was on except Aaron. So he was presenting there, so he basically was the one that had to show his face. All right. The goal was to fully acquaint everyone with the CCGO methodology, how to proactively find waste and accurately analyze it with the provided context, and most importantly, remediate it. This set the essential groundwork for driving adoption and making optimization a part of daily engineering life.
So we work with a lot of customers, and I think that the level of engagement we've seen with Bayer and their engineers is remarkable. Basically getting hundreds of engineers on a call, all thinking about cost and starting to drive that cultural shift and developing that cost mindset and so on. So kudos to you guys.
All right. So at the end of every session, we always leave with this note. Get inspired to have a look at Adaptive 6 for yourself. We're basically trying to encourage as many engineers as possible to look into to utilize the tool and provide and implement recommendations that are provided. And we'll go into detail of how those recommendations, with my example, how those recommendations are being applied in the examples I have later on. So we also started talking about it externally. As you can see here, I have Aaron. He's right here, by the way, giving a talk about Adaptive 6 and the success stories that we've had utilizing Adaptive 6. We also received interesting feedback from individuals as well with how Adaptive 6 was able to aid in identifying shadow waste and the guide on how to remediate it. Because oftentimes engineers don't really know, they don't have the context. So having Adaptive 6 provide that context, we realized was very, very helpful in achieving these objectives. So I want to share with you 7 real-world examples of things we've done with CCGO, hoping that these will be beneficial things for you to consider as you go home.
I think we should pay special attention to these because these are real-world examples within the infrastructure. So I think in terms of shadow waste, these are things that, as Michael mentioned, you could really be looking at, coming back home and seeing whether your infrastructure has any one of these inefficiencies.
Okay, so my first example is a pretty typical one. We all try to get engineers to do rightsizing, right? The main problem is that these tasks typically get deprioritized as they involve a lot of efforts from the engineers. Like they don't have anything else doing. The example we're seeing here is for database rightsizing, where in addition to highlighting it, we have provided a full technical context, as well as found the code that the engineers need to fix it, saving them precious time from having to look for it, as well as providing the actual Terraform code fix. In this case, change the red line to the green line. So the thing about Adaptive 6 recommendations is that you can do it in multiple ways. There is via the console, where it provides you with a guide on basically how to do it via the console. There's a CLI option. And then if you have Terraform code, it also shows you that Terraform code fix. And the thing that stands out for me is the one-click fix option, which, with the one-click fix, an automated pull request is initiated, which drastically accelerates the entire remediation process.
So I think this is fundamentally about making the remediation process as simple as possible for the engineers and really meeting them inside the tools that they use, whether it's GitHub, GitLab, Bitbucket, whatever they're using. So we sort of try to reduce that friction. So if you get the chance to it, I really encourage you to try and get your way around, like basically providing them with a pull request with those code fixes to really streamline that process.
All right. So we all focus on AI efficiency these days, right? It's a key topic for us too at Bayer. Here we are seeing an example of shadow waste in AI detected by Adaptive 6. When provisioning AI deployments like OpenAI, you can choose whether you use provision throughput and get discounts for reserved capacity or go with the pay-as-you-go. The thing is that if you don't go with provision throughput, you could waste money. And if you over-provision, you can also waste money. So the question is always on whether to go with it and for how much capacity. Over here, we can see that by analyzing the actual PTU demand over time, we can see that we didn't really need 50 PTUs, but we could probably settle for 1 or even go with a pay-as-you-go model. This was a huge opportunity for us. It eventually saved us hundreds of thousands of euros.
So this is a great example of AI shadow waste, where this could go unnoticed for a very long time. Like in this example, 50 PTUs is 50x than the one, or even completely removing it altogether. And it's also the fact that you might be doing this right now, but then 6 months down the road or 12 months down the road, the workload behavior actually changes. So it's all around not just doing this like as a one-time effort, but continuously monitoring your cloud and understanding if something has changed. So maybe you then need more capacity or less capacity, moving to on-demand and vice versa.
Right. So moving on to my third example of shadow waste is a case around storage accounts. Many times, engineers will opt in for premium storage, while in fact, they hardly even use the storage account, which was the case here based on I/O analysis. Oftentimes, they don't even know that they have to pay for premium storage. They just think, oh yeah, if I don't use it, then I'm not paying for it, which isn't the case really. All right. So we were considering the option of downgrading it down to the standard tier. After further investigation and a little back and forth with the engineering team, we actually decided to remove it altogether. Now, I really encourage you to be on the lookout for such cases that oftentimes get overlooked. It really saved us a lot. Another example of shadow waste is in the case of AI. A shot for every time I say AI. How many engineers typically opt in for using the latest and greatest models, such as GPT-5 to 5.2? In this case here, while in fact you can probably settle for a mini version. I know personally, like when I use Claude, I'll use like Opus 4.8 or something, and then at the, before the day is over, all my tokens are done. And I'm like, what'd I do? This is especially true for data processing workloads that do summaries, extraction, or classification of data. In most cases, you can move to mini and save up to 80% of the cost while keeping pretty much the same quality level, which is a big win.
One way to actually find such workloads which are a good fit for actually moving from premium to mini is to actually analyze the token usage. So if you see, for instance, that you have high input tokens and then you have low output tokens, so the ratio between them, the input to output is actually low, it typically means, not in all cases, but it typically means that there might be here a workload that does that sort of data classification or data summaries. For these kind of workloads that do data classification or summaries or extraction, the mini would, pretty much in most cases would be more than sufficient. So this is a good way when you come back home to basically look out for these type of potential workloads and optimize them.
Yeah. So my fifth example here that we encountered turned out to save us a lot is related to RDS, where you can choose between provision mode or Aurora serverless version 2. The Aurora option automatically scales resources as needed, which is great for cases where the workload behavior is harder to predict. Traditional RDS forced us to provision and pay, mind you, for peak theoretical capacity 24/7, whereas Aurora serverless version 2 dynamically scales compute in milliseconds, eliminating the waste of idle database hours during low traffic periods. As you can see here on the bottom right, I personally picked this one up. Place the issue with all the relevant contexts in the hands of the developer, in this case, through an email workflow, and this was fixed in a matter of days, which was a surprise to me because no one usually responds to my emails. Great savings with very low mean time to resolution, thanks to detailed context provided.
And with this example, just like with the AI one we saw earlier, there is provision mode, and then there is, essentially doing Aurora serverless V2, and essentially switching the two. It might make sense now, but then in a few months, you should keep on tracking that and seeing whether it still does make sense. Because over here, when the workload was actually analyzed, there were just random peaks, like you basically had a peak every now and then, like in read or in write. But really, if the workload behavior starts changing and all of a sudden you have far more reads and writes, then maybe provision is actually the way to go. So it's not just one-sided. You should always be looking at both sides.
That's right, yeah. So another fantastic example of shadow waste is a BigQuery billing model, specifically the choice between logical and physical. Logical storage is the default billing model for GCP, which charges based on uncompressed size of your data. Many times, engineers aren't even aware that there's a physical model. But physical storage bills you based on actual compressed size of data on disk. While the unit price per gigabyte for physical storage is slightly higher, BigQuery's compression is so efficient that it often reduces data size by a factor of 5 to 10. Using Adaptive-6, we were able to instantly identify specific data sets that had high compression ratios, making them perfect candidates for this switch. The tool did all the heavy lifting of calculating the exact break-even points for us. We had a very short meeting, less than 30 minutes. The engineer just wanted to know if he just wanted to confirm stuff, so it was less than 30 minutes, really. And in which we simply updated the single configuration from logical to physical on those targeted data sets, which by the time we were done, we immediately dropped our storage costs from those workloads with absolutely zero impact on query performance and engineering efforts. It's a perfect example of a hidden feature translating directly to massive savings.
And an additional note I would say here is that the cloud providers and also the SaaS and PaaS providers and AI providers, they keep adding new features all of the time or changing the price models, as we all know. So it's really important to be on the lookout as they introduce new capabilities, new configurations, and so on. This example right here, most engineers are really unaware of, that you have two billing modes specifically for BigQuery storage. And if you do have a lot of storage in your database, that could really accumulate. So this is a very important one. And by the way, why would even engineers tend to even think about these things, when they actually provision them, right? It's something that basically not every engineer has to know. It's very hard to now start doing the math of, physical actually costs less than the logical, but you need to calculate the break-even point to know exactly when you should actually do the switch. So I think this is really where, FinOps and, FinOps teams could really come in handy and basically, place this into the hands of engineers and making them informed and making this easy to remediate.
That's right. So my last example here relates to keeping production-grade storage redundancy in environments that simply do not need it. This is a common pattern. Aviv? I guess you'll handle
Yeah,
that.
so this is a common pattern we actually see across our customers, where they actually, Michael mentioned this before at one of the early slides, where you actually see that engineers keep the exact same configuration between production and non-production, right? We all get to see a lot of waste in these types of areas and so on. But why would you actually do that? Unless you have a very specific reason, maybe for compliance reasons or whatever reason it is, or you really need it to be identical, in most cases, you don't need that high availability within non-production. So this is a classical example of shadow waste of prod and non-prod mirroring.
So what's also nice is that it's an incredibly simple configuration change. But when you multiply the delta across hundreds of non-production storage accounts, the cost avoidance is substantial. It's a great and final example of why looking for shadow waste across your environments is so critical. So, these are some real-world examples where we saw a lot of value in CCGO. What I'd like to share with you next is ways to drive action.
So moving from finding ways to actually, getting it done and basically getting engineers to fix it, this is one of the biggest challenges within, the FinOps community. So I think that Michael's next 4 principles really demonstrate the roadmap on how to actually drive that change.
So, the way to really drive action is to provide full technical context to engineers, as well as empower them with AI that knows the infrastructure. So, every time an engineer sees an issue, he can consult with AI and get valuable insights that can ease investigations so engineers can understand the full scope and impact on their environment. Streamline resolutions. This gives engineers the guidance and confidence they need to deploy changes.
And if you want to take this to the next level, you could consider going with full automation, right? Automatically remediating some of these, or even driving agentic remediation with AI, whether it's automatically fixing it all, or whether it's with an engineer in the loop. This saves a lot of labor. You could also start with remediation or automated remediation within non-production environment, wherever you feel more comfortable. So this is really the leap between FinOps feasibility to actually driving CCGO action.
The second principle for driving action is critical. What is it? It's fixing the code when possible. This approach accelerates remediation by providing automated pull requests and code fixes, as well as prevents fixes from being lost or overwritten the next time the infrastructure's code runs. Focusing on the code is how we ensure the fixes stick.
And I can't stress this enough, because I see a lot of cases where folks are trying to remediate in the cloud, and then you basically have Terraform or other infrastructure as code running, and then it just overrides the change. Doesn't make sense. So you really want to focus on fixing it at the source. You may be able to do both, that's okay, but at least get it done within the source. And this is where you want to make it accessible for engineers as well.
That's right. So my third example is to tap into engineers' daily workflow, whether it's via email, tickets, Slack, Teams, Morse code, smoke signal, whatever. Sending that email or that message, or opening that ticket, providing the full technical context and remediation guidelines, I wonder how I'll do that in smoke signal, as well as providing a pull request is very helpful for accelerating the remediation process.
So we really have to meet engineers where they are, not just providing yet another dashboard, but actually meeting them within the tools they are used to. As mentioned, within the source code repos, within their CI/CD pipelines, wherever they engage. And this is really critical for adoption of a FinOps program at scale.
Yeah. So my last example is to shift left. This is left, right? Okay, yeah. Proactively alerting and preventing cost inefficiencies before they're ever deployed. This saves the labor of chasing down issues later and fundamentally embeds a cost-conscious culture in their development lifecycle. So those are the ways that we drive action at Bayer. But we aren't stopping there. To talk about what's next for us, I'm going to hand it back to Aviv to discuss the next frontier of optimization.
Thanks, Michael, for walking us through your experience with CCGO and these real-world great examples of shadow waste. So let's indeed talk about the next frontier in Bear's CCGO journey. So at the beginning of the talk, we talked about how there is, within the methodology of CCGO, it talks about waste, shadow waste, and then the next frontier is application inefficiencies. And this is really going to be the focus right now. So when we speak about application inefficiencies, we are talking about what's running inside the workload, what's running inside the application. As stated before, this unlocks millions of dollars in additional potential savings, because right now this is something that most of us just don't get into. We only look at the infrastructure. And even more important, when you have insight into the application itself, you get far more context. So even if you're looking at the rightsizing opportunity, but you don't know what the workload is actually doing, you could actually have a false positive, or the engineer gives you a pushback saying, this is completely irrelevant, we can't do nothing about it. So this is really important, and why you actually need to look inside the application. And typically, for doing so, you need to be using a runtime sensor to basically deploy, like a sensor, like a small app within the VMs themselves, within the pods. So let's cover some examples of application inefficiencies. And this is exciting because last year we had a talk here about shadow waste, and now we're talking about the next frontier, which is application inefficiencies. So typically, in order to find these type of application inefficiencies, you would use methodologies like profiling of the application itself and monitoring of the application. Some key examples of application inefficiencies include outdated application runtime. For instance, if you are running Python, I'm not talking about running it within the cloud like in a Lambda. I'm talking about running it within a VM, within a machine, and you're using an older version of Python. We're going to see that example and so on. Misconfiguration of the applications that are running inside the machine. That's a big one. Again, it basically doesn't exist nowadays in most tools, and this evades standard practices. Inefficiencies related to having applications that actually support ARM on x86. And then you're looking and you're speaking with engineers and asking, like, could we move this to ARM? But in reality, some you can very easily and some you can't. How do you gather that visibility? Inefficient libraries, inefficient code. So many cases, these application inefficiencies are harder to detect, yet very easy to fix, right? And this is important. Harder to detect, yet easy to fix than common waste. And the runtime sensor is really the way to uncover many of them. So the first example right here talks about detection within the VM. In this case, this is a Python application that runs within the VM, and it's running an older version of Python. So in this case, it's 3.9. And understanding that Python and understanding that version actually has a missed saving opportunity. In this case, by updating to Python 3.13, you could actually unlock dozens of percentages of cost savings for those type of workloads. Now, this is not because of end of life of Python 3.9, but because in 3.13 and up to that version, they introduced a lot of new capabilities and optimizations to optimize Python. Right? So this increases the performance, engineers love that, and it reduces the cost. And this is a good example of something that can only be done when you have a runtime sensor. Now, what if we could actually uncover the application even more? What if we could sort of have X-ray vision into the application, right? Beyond what we see when we look at the infrastructure layer, right? So the next example is an exciting one. What you see on the screen right now, this is called the flame graph, right? And essentially, you could think of this as sort of an X-ray into what the application does. So instead of just thinking in terms of 40% CPU or 60% CPU, you could actually unlock and understand what is the CPU doing. So what we are seeing in this graph right here, this is a Python application as part of an ETL, data processing. And you see that basically, you see 4 arrows right here. And you could actually see the functions that the CPU is running. So you could see it basically deals a lot with the processing of a JSON file. So you see it says like loads of JSON, and over there dumps of JSON. So around 50% of the time of the CPU is being used in this example to essentially analyze a JSON file. You could only understand this using a runtime sensor. Now, this by itself is not a problem. Okay, so 50% of the time, you basically have processing of a JSON file. But then you could actually see that it actually uses the default library in Python. It's called JSON to do that processing, right? And that library is actually inefficient. So by switching from the default Python library that does JSON processing to orjson, it's an alternative library, you could actually reduce the cost significantly by up to 40% and improve the performance by 66%. So this is a great example where a runtime sensor is really required, understanding what's going on within the application and uncovering a lot of potential savings. Now, this is not just for a niche case of a JSON file or a JSON library. This is relevant for a lot of the libraries that developers now use. If they use RE for regular expressions, if they use async IO, or if they have machine learning workloads that are using scikit. So really, across the board, when you analyze an application, there are so many opportunities and drivers for cost savings. The next example here, I think touches upon a common problem. So we all know the case like you talk with your cloud provider, they encourage you to move to ARM, right? And essentially, we all want to do that to basically get those cost benefits. The thing is, it's like sending you on a quest that you now have to go one by one for each of the machines, or sending the engineers for a quest, understanding what's running, right? And understanding whether that could actually be migrated into ARM architecture. So it's a big task. So typically when you see a recommendation from a cloud provider, move to ARM, and okay, but that's not really actionable. I don't know whether I could do it, whether not, what's the level of effort. But when you actually have a runtime sensor running within the machine, you could actually understand what's running. In this example right here, this is an Nginx web server. And Nginx actually has a support for ARM, right? It's basically very easy switch from switching your Nginx web server from Intel x86 to ARM. So by making that switch, you could then transition into ARM, of course, go through your standard testing, but this is a low-hanging fruit. And this is another thing that essentially a runtime sensor uncovers. The last example over here of application inefficiencies relates to a common pattern in many of our customers, that they basically have self-managed databases running inside their VMs. So we're not talking about managed databases like RDS, or BigQuery. We are talking about self-managed databases, like having a PostgreSQL running inside the machine. Now, many times engineers are not even aware of the configuration of that database running inside the machine. So by having that insight and understanding what's going on within the application, you could unlock a lot of savings. So in this case, the default setting for PostgreSQL is to essentially assume that you're using a legacy HDD storage. But while in reality, in modern environments, you typically use SSD. So the workload is actually unaware of the fact that you have SSD here. So by making a simple change, in this example, it's one configuration within the application. The engineer just gets there and changes the configuration of the setting, random page cost, from 4 to 1.1. You signal to the database that you could actually use SSD and avoid the penalty that it does for that. So this is another great example. The one last thing I would say here is that many times as FinOps people, we think about doing commitments or doing rightsizing and then commitments. But really, the way to go, or the suggested order by CCGO, is to essentially first find these application inefficiencies and basically optimize them. So then you actually reduce the CPU, the memory inside the application, the GPU, and so on. Then do the rightsizing, and only then do the commitment, right? So this is the suggested order. Summary.
All right,
yeah.
So in summary, you should adopt cloud cost governance and optimization in order to handle waste at scale.
Make sure to analyze both your cloud, code, and runtime. It's an important piece.
In addition to shadow waste, you should also focus on application inefficiencies. So that's all that we have. Thank you for attending this breakout session.
Hey everyone, producer Andrew here. Thanks for watching. Check out the rest of our channel for more FinOps content. Like, subscribe, and leave questions and comments for our speakers. We appreciate your support.